Good morning, students. We have been discussing so far on Fourier transform, Fourier inverse transform, then Fourier cosine and sine transforms, then Fourier transform of Gaussian distribution function, Dirac delta function, and all those things related problems. So we have discussed so far all those things related with Fourier transform. We discussed so many problems. Now we have come to the end. That is the application of Fourier transform, which is very, very important related to physics, especially when you are talking about quantum mechanics and heat waves. Wherever you find waves, the Fourier transform will exist, because as we discussed earlier, all the waves will be connected in terms of sine and cosine terms. You have a wave function, you have wave. These waves are can be connected in terms of sine and cosine terms. So wave is a combination of sine and cosine term. So sine and cosine term is nothing but Fourier series. So that's why always we go with Fourier transforms, especially when you are thinking about input and outputs. So Fourier transform is nothing but you have an integral which connects input and output in terms of waves. So wherever you find waves, especially heat waves and wave equation, you can think of only the applications of Fourier transform in physics. So we are going to deal with two applications. One application is related to flow of heat in an infinite and in semi-finite medium. Then another application is vibration of an infinite string and of a semi-infinite string. So this is related with Fourier transform. Then subsequently we will be dealing with Laplace. Okay. So the first application goes like this. As I said, the first application is nothing but flow of heat in a semi-infinite medium. And the temperature distribution U of x comma t. So this is called the temperature distribution. U which depends on position and time. So the temperature distribution which depends on position and time on a thin homogeneous semi-infinite box satisfies the infinite boundary value problem as given by. So this is your wave equation, heat flow equation. This is related with temperature distribution U, which is a function of position and time. So d squared U by dt squared equals c squared d squared U by dx squared, and c squared is the velocity of the wave, okay, in the medium. And see, look at the equation. One depends on t on one side, the another one depends on x. See here, so here it depends on t, here it depends on x. So that's why, as I said, the temperature distribution U is a function of x comma t, position and time. Now there are two boundary conditions. So there are two boundary conditions. One is the temperature distribution U x comma 0 equals your f of x when x is greater than 0, and another boundary condition is U 0 comma t which is equal to 0. So these two boundary conditions which we will be using later. So we are going to find the temperature distribution U of x comma t when t is greater than 0 and x lies between 0 and infinity. The given differential equation is given by this. So we have taken as it is the differential equations, and we are going to have the Fourier transform of those two differential equation, equation 1. See, this is your differential equation. We are going to have the Fourier transform, Fourier sine transform. We are going to take Fourier transform of equation 1. So f of s, Fourier transform of left hand side is equal to Fourier transform of right hand side. What is this one? So this can be written as, in terms of Fourier transform, this can be written as root of 2 divided by pi. This is as it is like this. Here you have taken Fourier sine transform. So this must be sine omega x dx. So we have now x and omega. X is in one domain, omega is another domain. See here, you have x and omega. We have one domain to another domain. Fourier transform exists only between these two domains, Laplace also. So here as I have written as it is, sine omega x dx, which is equal to, you pull c squared root 2 pi out, as it is constant, they are constants. You write as it is in terms of Fourier sine transform. So we have written like this, sine omega x dx. Any doubt? Okay, so this term can be written as Fourier sine transform of omega t. We know already. So this term is termed as Fourier sine transform of omega t, left hand side. Now you just right hand side, you consider this is with respect to x. See here, we are going to differentiate with respect to x, but here we are going to with respect to t, but t is not here. So here with respect to x, but x is here, easily you can differentiate. So after differentiation we will find out. So you are going to take only the right hand side alone. You are going to take the differentiation. 2 times we are going to differentiate. First we will differentiate once. So that will give me du by dx. Sin x we are going to differentiate, that will give you cos omega x into omega. Again you are going to differentiate with respect to x, that will give you minus sin omega x. This will become minus sin omega x dx, and u x comma t sin omega x dx with one minus sign. So minus omega square c square. And we are going to term this as, already we know that this will be your Fourier sine transform of omega t. See here. Similarly, this one termed as Fourier sine transform of omega t. Is it okay? So now we can replace. We can replace as, see here, you have d by dt, and this will be your f of s omega t. And this is as it is minus omega squared c squared, and this side you have f of s omega t. See, minus omega squared c squared f of s omega t on right hand side. Left hand side you have d by dt f of s omega comma t. Is it okay? Now I can take this term to left hand side. So that will give you d by dt f s omega comma t plus c squared omega squared f of s omega t equals 0. So the general solution of this, the solution of this equation is given by this. You are going to assume this solution. See, the general solution of this is given by this. How to check whether this solution is correct or not? One way is you just differentiate with respect to t, substitute here, you will get 0. So this is one way. Usually students will do. You just differentiate with respect to t, and you substitute here in this equation, you will have 0. That means it satisfies. Okay. Now at t equals 0. So we have lot of conditions, boundary conditions are given earlier. See here, earlier x comma t. See, u of x comma t at t equal to 0, this becomes f of x. Look at the boundary condition at t equals 0. See, thermal distribution u comma x comma t, u which depends on x comma t equals 0. So we can have one boundary condition. So t equals 0. When t equals 0, your f of s omega comma 0, which is equal to, when t equals 0, this becomes 1. So you have a omega, amplitude a omega. So a omega can be written as this. Okay. Now, hence equation 4, this equation becomes f of s omega comma t. Instead of a omega, you can substitute f s omega comma 0 e power minus c squared omega squared t. Is it okay? I have replaced a omega by f s omega comma 0. Is it okay? Very simple one. So equation 4 becomes equation 6, exactly like this. Now another initial condition, u comma x comma t equals f of x, which has been given in the problem. So now apply Fourier transform on both sides of equation 7. So you have f of s u comma x comma 0, which is equal to f of s of f of x. Now this can be written as Fourier sine transform of omega comma 0, which is nothing but your f s of omega, which is equal to, I am going to term as g of omega. So your f s omega comma t, which is equal to, stop on it. So you have f s of omega comma t, which is equal to, instead of this you can substitute g of omega. So in the earlier equation it was there. So you can substitute g of omega e power minus c squared omega square t. Now apply inverse Fourier sine transform on equation 9. You will have the complete solution. So inverse Fourier sine transform of this is equal to, right hand side also you have to apply. So which is equal to inverse Fourier sine transform of this. So this can be written as Inverse Fourier transform is nothing but your E of x comma t, which is nothing but your thermal distribution function. So that we want. So thermal distribution function is given by root of 2 divided by pi, this term, e power minus c squared omega squared t, sin omega t, so sin omega x d omega, which is your required solution. Any doubt? So now we'll go for the second application. Any doubt on the first one? Okay. The similar procedure. So application of Fourier transform. Now we are going to solve this one as string, a waves in a string, in an infinite string. Okay, in an infinite on both ends. Now the equation is given as d squared u by dt squared, which is equal to c squared d squared u by x squared. As usual, u depends on x comma t, as usual. This equation satisfies when a string is fixed at both ends. So this is infinite form. So boundary conditions are given as this. So these are the boundary conditions. U x comma 0 equals f of x when x lies between minus infinity and plus infinity, and du by dt equals 0. So this is another boundary condition at t equals 0 when the string is at rest. When string is at rest, the differentiation of the function which is equal to 0. Now you just write as it is this equation. The same procedure, we are going to follow the same procedure. We are going to apply the different boundary conditions. Okay. Now the first one is we are going to take the Fourier transform of this equation on both sides. Just take the Fourier transform of this equation on both sides. So we have taken now. Now the Fourier transform of this will be, we have 1 by root 2 pi d squared u by dt squared e power minus I omega x dx. Doesn't matter, in last problem we have taken as root 2 divided by pi. Can you remember? However, both will get cancelled. Doesn't matter. Okay. Root 2 divided by pi in the last problem we have taken. And some other books you may find 1 by root 2 pi. Okay. But both will get cancelled. Doesn't matter. Okay. We will see. However, the convention that we are going to apply is 1 by root 2 pi for all physics problems. Okay. For all quantum mechanics we will go only with 1 divided by root pi. Okay. So now Fourier transform of this one will be d squared u by dt squared e power minus I omega x dx, which is equal to 1 divided by 2 pi d squared u by dx squared e power minus I omega x dx. Okay. Now I am going to keep this as d squared by dt squared. I have pulled out. Remaining terms I can keep it inside. Okay, as usual. Then here, with respect to x, we are going to differentiate. Here also x is there, so you can differentiate easily, as usual in the last problem. So when you are going to differentiate e power I omega x, that will give you minus I omega. You are going to differentiate. You are going to differentiate twice. So that will become minus I omega multiplied by minus I omega. So you have minus I omega whole square u, which depends on omega comma t. Okay. So now, where this is termed as u of omega comma t. This is termed as. So we are going to keep it as u of omega comma t, which is equal to 1 divided by root 2 pi u of x comma t e power minus I omega x dx. I repeat, this is termed as u of omega comma t. Fourier transform of this will be u of omega comma t. So we are going to replace this term as u of omega comma t, this term as u of omega comma t. Okay. So we have d squared u by this term we are going to replace with u of omega comma t. U of omega comma t. And right hand side already we have found out right hand side. Right hand side is nothing but c squared minus I omega whole square e of omega t. See here. Now you just take this term to left hand side, you will get which is equal to 0. This is your quadratic equation. The solution of this equation is given by this. We can find out a and b using boundary conditions. Again, as I said earlier, we will have to differentiate 2 times and substitute here, you will get 0. So you can check whether this solution satisfies the differential equation or not. You can check it out. So where a and b are constant, whose values are found by boundary conditions. So now differentiating equation 3. Just differentiate equation 3. Because boundary condition goes du by dt equal to 0 or t equal to 0. boundary condition says in the problem. Okay, du by dt equals 0 at t equals 0. So you just differentiate. You will have minus a c omega c minus a c omega sin c omega t plus b c omega cos c omega t. As it is given as du by dt equal to 0 at t equals 0. You substitute t equals 0 here. First, right hand side. If t equal to 0, this one will go off. You will have only cos 0 is 1. So you will have dc omega. dc by dt equals also 0. Okay, so we are going to substitute du by dt equals 0, which implies that bc omega equals 0. So which says that b equals 0 because c cannot be equal to 0, omega cannot be equal to 0, and only thing is b can be equal to 0. If b equals 0, you substitute here. B equals 0. You can get the value for u of omega comma t, which is equal to a cos c omega t. Is it okay? Up to this. Now using first boundary condition. So we have used the second boundary condition earlier. So this is your second boundary condition. Now we will use first boundary condition. First boundary condition goes u of x comma 0, which is equal to f of x, which is equal to f of x. Taking Fourier transform on either side. You are going to take the Fourier transform of either side. So just take the Fourier transform of either side. That will give you f of u comma x comma 0, which is equal to the Fourier transform of f of x. So Fourier transform of this one will be your e of omega comma 0. Fourier transform of this one will be your f of omega. We know already. Now, so we know that just now we have found out the solution. So we know that u of omega comma 0 equals a cos c omega at t equal to 0. So your a can be termed as f of omega. So instead of a, you can substitute f of omega in the solution. See here, we have the solution a. We are going to replace with f of omega. A is termed as f of omega. So e of omega comma t equals f of omega cos c omega t. So this is your complete solution. This is your complete solution. Now taking the inverse Fourier transform. After getting the solution, you will have to take the inverse Fourier transform as we have done in the last problem. So taking the inverse Fourier transform, we can get the function u x comma t from its Fourier transform u of omega comma t as e of x comma t, which is equal to 1 divided by 2 pi minus into plus infinity e of omega comma t e power I omega x d omega. So this is your inverse Fourier transform. So ordinary Fourier transform will have minus sign. Inverse Fourier transform will have plus sign. Now instead of u comma omega t, you substitute this. You substitute this. Instead of u comma omega t, you substitute which you have obtained earlier as solution. So this becomes exactly this expression, equation 8. Okay. Now 1 by 2 pi. See here, cos c omega t can be written as e power I c omega t plus e power minus c I omega t divided by 2. And you have e power I omega x. You multiply. So this term with this term, and that will give you f of omega e power I c omega t multiplied by this term will give you ct plus x. Then this term will give you I omega x minus ct, and separate the term with the integration. You can separate. Correct? So this multiplied by this will give you I omega, you pull it out. So that will give you ct plus x. Similarly, you can pull I omega out, that will give you x minus ct. You can integrate on separately. Correct? You can integrate. So this term, I have integrated this term as exactly like this, and this term I have written exactly like this. And what is the Fourier transform of this? Which is nothing but your inverse Fourier transform. It's nothing but your f of x plus ct. See here, property x plus ct, and this will be your x minus ct. So this is your complete solution. Complete solution of the waves in the string in an infinite way, which is nothing but u x comma t equals 1 by 2 f of x plus ct plus f of x minus ct. So this is the required solution. Okay.